Check, check. Please come in. Hello, everyone outside.
Do I get a pointer? No, it's fine.
Are we done? Okay, let's start with the afternoon session. So the first talk will be by Wojciech Kotlarski from Dresden at the moment still, and he will talk about flexible decay and automated computation of scalar decays. So of 25 minutes, after 20 minutes, I will show you 5-minute warning. Okay?
Okay.
Yeah.
Okay. Thank you very much for the opportunity to know. Okay. Thank you very much for the opportunity to come back to Corfu after all those years. And I'm going to talk about the work that I done with Peter Afron, Dylan Harris, Dominic Stockinger, and Alexander Voigt. And this is going to be about code that computes scalar decays with a special emphasis on Higgs boson decays. So just one slide of the motivation. Maybe I will move away from the speaker. Just one slide of the motivation. So as you know, many BSM models predict existence of new scalars, and the way how they decay is very important for designing collider searches. And any kind of realistic BSM extension must contain also a standard model like Higgs boson. Since LHC was unsuccessful in finding any kind of signals of BSM, the one Higgs that we found should be our window to the beyond the standard model physics. And the fact that your Higgs should be standard model-like puts a very strong constraints on any kind of BSM models. But to be able to apply those constraints, you actually need a highly accurate prediction for the Higgs branching ratios. Since, as you can see here, just for illustration, the precision with which we measure the Higgs branching ratios at the LHC is actually quite impressive right now. Because the talk will be slightly technical and there will be some discussion about the computer code, I cannot blame you if you space out at some point. So if there is just one slide that I would like you to take from this talk, is basically this, a short advertisement. So if you have a BSM model and you would like to check its Higgs sector, but you don't want to actually do the calculation by yourself, so this is the place where our code comes in. So you can get all the nice stuff that I will be discussing today, basically for free. Broadly speaking, the flexible decay is the fully automated scalar decay evaluation. It provides you with a fully automated scalar decay evaluation in the arbitrary BSM model. So just during the development, we have tested this code with the standard model, with the real singlet extended standard model, type 2 HDM, DMSSM, and the minimal asymmetric supersymmetric standard model. But basically, any model that you can write as a renormalizable field theory should be fine. The code works as an add-on. Sorry. On the flexible SUSY spectrum generator. I will talk about this in one of the further slides. and basically requires no extra configuration from the user. So if you have ever run a flexible SUSI, then you basically don't have to do anything. For many models distributed with flexible SUSI, so the one that we know that it works, we have already enabled it by default. So this is just adding this line. And the particles for which you want to compute decays are given with the following way. The default is to just include the Higgses, but here is an example how you could change it to also introduce, to also get the decays for the squark and leptons. So this is just as an example in the NMSSM, and then you run flexible SUSI as before. Now, generic decays are handled at the leading order, which means either this is a tree level or loop-induced. Either this is a tree level for the process that already exists at the tree level, or one loop level for the loop-induced processes. And as I said, the special treatment is applied to the scalar and pseudo-scalar Higgs decays, where we apply known corrections, known higher order corrections from the literature. And what we get at the end is the code which has a precision comparable, although not quite exactly the same as HDK. So technically, the way how it works is that you automatically generate all the 1 to 2 amplitudes, and all the types of the final states are handled. So scalar, fermions, vectors. Most color representations are handled. There will be some remark about the limitations of the code in this respect. In the calculation, you use the MS bar or DR bar vertices with pore masses on the external lines. And the example application that I will show you later is fermion decays in the SUSI, or Higgs decays to non-standard model particles. And as I said, there's a special treatment for the Higgs decays to the standard model particles, so that this also includes the channel, which is very important phenomenologically. So single and double off-shell decays into the pair of gauge bosons. Now, when it comes to the loop-induced decays, at one loop level, you have 10 topologies. So the way how we technically did it is that we generated analytic expressions with at the generic level in the finals language, with scalars, fermions, and vectors, and you have a large number of those routines for all those diagrams. And then once you have a concrete model, you can match the particle content of your concrete model to those generic expressions, and this is done in a way that the user never have to run finals and form calc, because all of this is pre-generated. And internally, we are using the color math package from Ms. Siodal to handle the color factors for all the diagrams. Now, the one important part is the choice of the renormalization scheme that we selected for this. So there are basically two ways how we could go about it. So we could do the onshore scheme, which is most natural, but this is not how spectrum generators work, and this is also not the best choice until you actually find a given BSM theory. On the other hand, the typical way how the spectrum generators work, so on the MS bar, on the DR bar scheme, you are getting a non-decoupling effects. And since now we kind of expect that the BSM physics mass might be heavy, then this would not be a perfect choice. So what we opted for is something that we name for ourselves the decoupling scheme. So the scheme which has a explicit decoupling property. So the BSM equivalents of standard model parameters are set to the standard model MS bar values, while the actual BSM parameters are defined in the MS bar and DR bar scheme. So the code by itself is agnostic to the scheme choice, but the higher order correction from the standard model, higher order correction from the literature can only be taken over if you are working in this decoupling scheme. Now, the other a side advantage of using MS bar or DR bar scheme as opposed to, for example, the onshore scheme is that it allows you to for an easier connection between Higgs branching ratios and observables like vacuum stability, which are things which are at least in some ways related. And here's an example how this decoupling scheme works in practice. So there's many lines, but there are three types of lines in the ASP. So there is the standard model line, there is the for a given channel, there is the line for the MSSM in the decoupling scheme, and there's line for the MSSM in the non-decoupling scheme. And what we do here is that we are in the CMSSM, we increase the scale of the SUSY particles from 200 GeV to 250 TeV, which also translates to the increase of the Higgs mass. And what you can see here, for example, is that this is the H2BB bar in the standard model. This difference here is a genuine BSM effect. And once the SUSY becomes heavy, all the curves converge. So on this plot, in this scale, actually the decoupling and non-decoupling scheme, they both converge to the standard model. But for example, for the Higgs to gauge bosons, you can see that the decoupling scheme does converge to the standard model value for the heavy SUSY masses, while you get a discrepancy with the non-decoupling renormalization scheme. So basically, what it actually does, it interpolates between the BSM and the standard model. So you are safe when you want to push your model to the very high scale. One word about the higher order correction that we have implemented. So as you already seen a few times at this conference, if you look, for example, at the Kappa framework, then you can see that the precision of the measurement of the, sorry, this is round 2, of this Kappa parameters is already at the level of 10 to 20%, both for the Atlas and for the CMS, while for the high luminosity LHC, we are expecting to reduce this uncertainty to below 5%, which means that any kind of code that computes Higgs decays, for it to be useful, you actually have to apply at least the standard model higher order corrections. So this is the non-exhaustive list of the higher order corrections that we have introduced. So as I already mentioned, you have a single and double off-shell decays into gauge bosons. You have the QCD corrections to the top triangle loop up to 4-loop order. You have the 2-loop corrections to fermion and scalar loops to the H2 gamma gamma. 4-loop QCD, 1-loop QED, and even 2-loop mixed QED, QCD to H2PQ. And the treatment of the H2PQ channel is similar like in the HDK, which I will mention briefly in a second. One last kind of technical point is about the world identity and the bad things that might happen. This is, as you know, the generic form, the generic Lorentz decomposition of the scalar to the vector amplitude. And if the world identity holds, then if you use the physical condition for the polarization vector, and then you apply the world identity, you are getting this relation between the F eta and F21 form factor. Now, the bad thing that might happen is that this is trivial in the on-shell scheme or in the unitary gauge, but in the gauges other than the unitary and non-on-shell normalization scheme, this relation will get broken by higher order. So you are getting 3 sets of diagrams. Two first one fulfill the world identity automatically, while the third one is problematic. So what happens here is that you have this H2 Goldstone coupling, which has this form, and because this is the only diagram in this set which has actually this lambda coupling, it's obvious that if the lambda is kind of free parameter, then you can move that this diagram can break the fulfillment of world identity because it only contributes to the F eta form factor. And in the on-shell scheme, this hangs on the fact that also the physical momentum is equal to the Higgs mass. So this mh square is the on-shell mass. Now, so the way how we chose to do it was that we actually checked if the two calculations where you assume that the word identity holds and you eliminate either f eta of or f21, give the same result, and if the result is too different, then we actually print a warning, so you could know that that the bad thing happened, and that maybe you should have a look at this. Okay, so now, because all of this is in the framework of the flexible SUSY, then I will just briefly describe you what is a flexible SUSY. So flexible SUSY is a spectrum generator, which probably does not tell you much. But if you know codes like, for example, 2HDMC or Spheno or soft SUSY or Suspect, which calculate the masses and various observables for those models, then think of the flexible SUSY as a 3D printer that can print you those generators like Spheno, but for arbitrary model, not only for the MSSM. And this all relies on the known generic results from QFT. So the idea is that you just don't do things that you don't need to. This is all known, so you shouldn't have to actually get your hands dirty. And this streamlines the BSM phenomenology and hopefully allows you to focus more on physics than on looking for bugs. Unless you find a bug in our code, then we would be very happy for you to let us know. And the way how it works is that we start from Sarah, which was developed by Florian Staud, which provides you the analytic calculation for a given model, so like particle content, Lagrangian, Pole equations, self-energies, mass matrix, and so on. And then flexible SUSY will create you a C++ code, which would compute one loop masses and mixing in some models with higher order corrections, and certain observables like G-2, EDMs, like mu2 gamma, B2S gamma, now scalar decays, and soon also the other flavor violating observables like lepton conversion on lepton to free lepton decays. If you would want to use it, there are some simple prerequisites that you need some packages, which like Eigen, Boost, GSL, they should be in your distribution, in your Linux distribution. You need Mathematica or Volcam engine, you need Sarah, and you need a C++ 14 compiler. So this is the requirement for this compiler. And also for the decays, you would need some dedicated loop library. So nowadays, now for us, it's either Loop Tools or Collier. Current version of flexible SUSY is this 2.61, and you can get it if you click on this link in the PDF, and everything should work on Linux, Unix, so this includes macOS and hopefully Windows, but this is always hit and miss. And this is the example how you could run it. So, for example, this is the creation of the 2HDM. Then you configure it. Here is like a simplest example. There are other options that you can get after typing help and other libraries that you can link with. Then you make, which will call Mathematica, and then will compile the C++ code, and then you can just run it. Like this is the example. So unless you want to do something fancy, this is everything that you should need to do. And this is what you get in the end, at least when it comes to decays, because the output is in the SLH format, so there's a lot of stuff there written. But this is the kind of output that you would get. You get some block which contains some information about which version of what was used and what kind of models. And there is the decay block which tells you that the decay width for the 25 gigs is this. And here are the channels with the branching ratios. It doesn't get more complicated than this. Okay. Just before I go to the tables, with more accurate comparison, here's a comparison between the plot that we did with our code and the picture from the LHC cross-section working group. So if you look at this, okay, granted this is logarithmic scale, so it's always easy to hide any kind of mistakes. But if you just look at this by eye, then they look they look fine. So The only difference are those peaks, which come from the switching between the off-shell decays to W and the two-body decays, because the LHC working group is using the prophecy for F, which is a code that always deals with a 4 lepton final state. So that's why they have no threshold. So that's why you don't see these kinks. But other than that, from this you can see that at least visually for the standard model, everything works fine. Now, some more detailed comparison, because we are talking about precision calculation. So here is a comparison of the Higgs decays in the CMSSM between flexible SUSY. There are two versions of Saras-Fino. I will just say in a second why there are two. There is soft SUSY and SUSY hit, which internally uses HDK. So a few things to note is that overall the agreement is quite good, apart from some outliers which we track down and we can explain. So for example, in soft SUSY here they use the strict on-shell calculation, which has an explicit term which is log NB over MH, where in other codes this log is resummed by using the MS bar coupling for the bottom U cover. So that's why this is the outlier. The generic feature is the H2Z gamma in Saras-Fino seems buggy, because it always produces some weird numbers for any kind of model. So here there are two versions of Saras-Fino, because here you have the tree-level calculation plus higher order standard model corrections, while here you have the actual one-loop calculation with all the effects. So in principle, we would be interested only in this column, but only this version calculates this Higgs to the gamma, which we wanted to compare with. But yeah, it always produces some weird numbers, so we probably should not pay too much attention to this. And there's a difference in Saras-Fino in the treatment of the decay to VV, in that they only include the single off-shell decays, while all the other codes include the double off-shell decays. This is not who is better or worse. This is more about the way how you define your observable. Now the comparison in the MRSSM, which is minimal asymmetric supersymmetric standard model, sorry about that, which I think is more interesting in the sense that here you have all those codes that can work with the CMSSM. So it's really a no-brainer to find the code that would get you the decays in the CMSSM. But this is the part that shows the strength of those codes, that those are only two codes that are able to compute decays in the arbitrary model. Like in this case, it's this MRSSM. And if you have another model that you're interested in, then you could also get the same for it. When it comes to the precision of this comparison, here most of the remarks from the previous slide also hold. So the H2Z gamma again seems buggy, and with the case of the other channels, the precision is all the comments from the previous slide still holds. Overall, the agreement is not so bad if you think about that those are different codes where the calculations are organized somewhat differently. The last thing to mention is that apart from the Higgs, we can also do decays of other scalars. Like for example, in this case, this was for the bottom quark. Here we compared with soft SUSY and Saras-Fino and SUSY hit. In this case, SUSY hits has some higher order corrections, which we have disabled, not to make SUSY hit look bad, but just to compare apples with apples. So if you are sensitive to those corrections, then you are welcome to use SUSY hit. But if you are only interested in the tree-level decays, as we have for the squarks, then you could also use flexible SUSY. And now one slide about the limitations. So as currently, the decays of fermions and vector bosons are not supported, so only decays of scalars. And also not all color combinations are supported. So this is only the case for the octets. So some combinations with octets work fine, like 8 to 33 bar, or 8 to 83. But the one that doesn't work is the 888. In general, we cannot yet handle. Cannot yet handle the cases where you cannot decompose the vertex into a product of a lone structure and a color structure. So stuff like 40 gluon vertices will not work, and only 1 to 2 decays are possible, with the exception of the scalar Higgs to ZZ and WW, where we have hand coded the single and double off-shell decays, assuming standard model decay pattern. And the last slide about the code organization and how you can get help. So all of this is a code written in the relatively modern version of C++ with a heavy use of template metaprogramming. It's written partially in Mathematica, partially in C++. There are some Fortran bits that were taken from older codes, and some stuff that is supposed to glue it all together, like Makefile and Shell. The development is done in public on GitHub, so you can have a look and sometimes have a laugh at our expense on the stupid stuff that sometimes happens there, and the comments that someone left in the code because he forgot to clean them. There's a large collection of unit tests which are triggered on every commit for the repository, so that you can be sure that if you download something that it's not totally broken. And if you have any problems, just please file an issue. We will try to help you as much as we can. Conclusions. So flexible decay is a powerful tool capable of computing decays of scalars in arbitrary model. As I mentioned, the Higgs, because it's special, it's treated in a special way, such that you get a precision close to H decay, although of course not quite the same. You can get the code by visiting this link, which you can click in the PDF. The current version is version 2.61. And we will try to help you because if you have any problems, because the thing is that writing a generic code is hard, and only with users which come with real life problems you can actually make the thing better. And the future plans will be to finish the decays of the Fermions and vectors, and also add the genuine one-loop corrections to 3-level decays. And I hope that in a foreseeable future we could actually get to it. Okay, thank you very much.
Thanks a lot, Wojtek, for this very nice, interesting overview. Other questions? I would encourage people on Zoom to raise their hands. I don't see any hands at the moment. So are there any physical hands in the audience? Okay, maybe Gustavo first.
You mentioned that your program applies to a special class of 2 Higgs doublet models, in particular SUSY type 2, whatever, you know.
Yeah.
But what about the most general 2 Higgs doublet model, where there is no idea of natural forever conservation and all that?
That's not a problem.
It doesn't. It applies still. I see.
Yes.
So it should emphasize that, because that's a big thing, you know. Type 3, the one that doesn't have any.
The only problem with this is that we don't have created such a model, so you would have to write it. So we have experience with the aligned 3 Higgs doublet model.
Yeah.
Because the problem with those models is that the way how spectrum generators work is that at some point you have to match your BSM theory to the standard model. So you have to write matching conditions of your model to the standard model. So how one U-cava is expressed by the other. So this is kind of, it's not complicated, but it's some work.
Okay.
But there shouldn't be any problem.
One can use your code, but then take into account certain modifications to adapt to a more general theory, right?
Yeah, so yes. So what I mean is that we have some set of models that we have created. But if you would come with your own model, like for example, fully generic to HDM,
Yes.
there is some small piece of like a code that instructs us how to what is actually contained in your model.
Okay.
Okay. Lana, I think, had a question. No?
Technical question concerning this colors code that you will use. Does this only under quotes handle octets and triplets, or can you use, for example, as things like a sextet?
So for this, we are limited by what the code from Malim Siodal is.
I'm referring to this code.
Oh, I think that sextets are fine, but I will have to check it.
Is this code public?
Yes, it's public.
Thanks.
Okay, I think if there are no more
There was
super,
something-
Jan, okay, quick, please, quick. The organizers told me to stick to
You
the
will
time.
understand why I asked this question. Can you handle three Higgs doublet model with some discrete symmetries or whatever?
Yes, of course, the best of the multi-Higgs doublet models, yes.
Okay, so let's do it.
Okay, very good. I think we have to continue. I mean, Wojtek is here for some time. You can ask him. So we should go to the next talk, which is in person or online. I don't know. In person, a real person. Very good.
Sigma 36 presentation. It's the
Okay, very good. I think we can start. So we are here now about exploring multi-Higgs models with soft broken large discrete symmetry groups by, if I read it correctly, Miguel Levy. And you have 18 minutes. After 14, I give you a warning. Okay? All right.
all right. Right. First of all, let me thank you for the opportunity to present this talk, and then I'll be talking about exploring multi-Higgs models with softly broken large discrete symmetry groups, where in particular we'll be focusing on a sigma 36 symmetric 3 Higgs doublet model. Do I do this? All right, so the talk is outlined as follows. We first try to motivate the work. We'll then go through the features of the symmetric sigma 36 3HDM, and then we will show the results of introducing soft breaking terms in such a way that we preserve at least one of the web directions of the symmetric 36 3HDM, which is the way we found to try to preserve some of the characteristics we have in the symmetric case. Sorry. And then we'll try to, we end up with a summary. So we all know that the standard model cannot be the ultimate theory of physics. And so we need beyond the standard model physics, but despite of all of the efforts of the experiments, these are still not found. And so without any compelling evidence for the shape of the beyond the standard model physics, we need to explore different avenues. And so one of the most common paths to do this is to study extended scalar sectors. Now, these are very easily motivated by UV completions, but they do come with a problem, which is introducing a large number of free parameters. One of the other common paths is to introduce flavor symmetries. Now, these actually deal with the problem of the proliferation of free parameters, and by doing so, they also increase productivity. But this is usually a double-edged sword because the strict predictions that the flavor symmetries give can then run in conflict with experiments. In terms of extended scalar sectors, two Higgs double models still reign supreme, but three HDMs are gaining some traction. Aesthetically, they have the same number of generations in the scalar and fermionic sectors, but in practice, they open up flavor symmetries which have triplet representations. And so if we look at symmetry-constrained 3HDMs, we can use small groups. These still retain a lot of the flexibility we have in 3HDMs, but they do this by not being very much constraining. Now, if you use large groups, then these are highly constraining, not only in the number of parameters we have in the theory, but also in their predictions. And so what we do is we study softly broken large groups in such a way that we introduce flexibility into our models and try not to take away all of the predictions of the symmetric case. So in this case, what we call large discrete symmetries are basically, for the 3HDM, it would be a symmetry where all of our Higgs are in a triplet representation, and thus the scalar potential has a trivial quadratic part, and then the quartics depend on the group we choose. Now, if we want to introduce operating terms, then we have to add 9 new parameters, and from there, I mean, for any specific point in parameter space, it would be trivial, straightforward to just do the explicit calculations and see what are the results we obtain. But this is not very enlightening. Indeed, we don't expect all of these soft-breaking terms to be on equal footing. I mean, some can drive structural changes of the potential or the minima, but others can lead only to numerical deviations. And so this is basically what we try to do. We try to tame the large number of soft-breaking parameters we have in such a way that we introduce flexibility into our model, but we do so in a controlled way, and then study its consequences. All right, so let's review the sigma 36 symmetric 3HDM. The scalar potential features automaticity invariant, and thus we have basically 4 real parameters. From these three are actually SU3 symmetric, and it's the last one that selects the sigma 36 subgroup. And in this particular form, what we find is that if we select lambda 2 to be positive, then we are protected against charge breaking minima, and we are free to just study neutral minima. And so if we do to its simplistic shape, we can basically find that this potential has a very rigid minima structure. Indeed, its minima can only be of type A or type A prime, or depending on the sign of lambda 3, it can also be of type B or C. So this basically means that we have 2 distinct phenomenological situations, depending on the sign of lambda 3. It basically means that the points A and A prime and B and C are basically overlapping and degenerate. And so we can use this to try to find the predictions that this flavor symmetry does on the scalar masses. And we see 2 different things. The first one is that due to the trivial quadratic part, we have automatic scalar alignment, which means that the identification of the standard model like Higgs is trivial. And we also find pairwise degeneracy in the sense that all of the charged scalars are degenerate, and we are left with 2 tiers of pairs of neutral Higgs which are degenerate. So small h's are degenerate and the big h's are degenerate. And so in terms of a summary of the symmetric model, we have a very rigid minima structure. We know that spontaneous CP violation is impossible. We have automatic scalar alignment, the pairwise degeneracy, and we actually don't even have that much freedom in terms of our 2 different tiers of neutral masses, since they are related by a factor of square root of 3. And not only that, but since no alignment actually fully breaks the symmetry group, this also means that the lightest non-standard Higgses are stable against decays into the standard model 1, well, looking only at the scalar sector. And so we want to introduce some flexibility into our model. And what we do is we choose to preserve one of the symmetric minima of, we add soft breaking terms in such a way that we preserve one of the VEP elements of the symmetric theory. And so we are left with a question, which is how can we preserve, or what are the conditions to preserve one of the VEP alignments? And so if we look at the symmetric potential, we go to the extremum conditions and we find a very simple relation between the quartic terms and the bilinears to do this. But if we introduce soft breaking terms, parameterizing them as a matrix, then our potential obviously changes, and so will the extremum conditions, and the relation we find no longer holds. But if we require that the full potential and the symmetric potential have the same vacuum alignment, then we recover a modified version of our relation, and when we plug them into the extremum conditions, we can find a very simple statement about how to preserve the VEP alignment in the softly broken case, which is the VEP alignment must be an eigenvector of our soft breaking matrix. And so, just to clarify this with an example, we take, for instance, point C, which is one of the minima of the symmetric case, and we decide to parameterize our matrix, our soft breaking matrix, as 3 eigenvalues and 3 eigenvectors. And so, since we want to preserve one of the VEPs, we already know one of the eigenvectors, since it must also be an eigenvector of the soft breaking matrix. And all that is left to do is to find an orthogonal basis to N1, which we choose to be this one, and then we can define our remaining eigenvectors as general rotations of these spaces. And thus, by doing this, we find that from the set of 9 parameters which we could introduce as soft breaking terms, we actually have 5 which are able to preserve the VEP alignment of the symmetric situation. If we further impose that we also want to retain the magnitude of the VEP, then we have to set our rescaling parameter to 1, which leads to a vanishing U1, and then we have 4 parameters, 4 soft breaking parameters, which are able to preserve not only the direction of the symmetric minima, but also its magnitude. And these are basically sigma, delta, which are the sums and differences of the eigenvalues, and 2 rotation angles. So by doing this, we can then just, this is easily generalizable for the other minima just by a suitable redefinition of the basis vectors, like this. And so we can easily, since we are preserving one of the minima of the symmetric situation, it's a fairly simple procedure to see what are the differences in terms of the physical mass, physical scalar masses. And the features we find is that we still retain the scalar alignment because so we still retain the scalar alignment. We have the unambiguous identification of the standard model like Higgs, and since we are setting U1 to 0, we also leave the Higgs mass untouched. We find something which is particularly interesting, which is although we have 4 different parameters, soft breaking parameters, the masses are actually only a function of 3 of them. And this seems to suggest that the orthogonal, the perpendicular direction of these 2 rotation angles should adjust additional features of the softly broken potential without changing the masses. We see that the degeneracies we have in our symmetric case are lifted, but they are not free. Indeed, the splittings we have in the lighter pair are completely identical to the splittings we have in our heavier tier of neutral Higgs. And one other interesting thing is that although the A and A prime and B and C points are actually overlapping in the symmetric potential, these are no longer, we find that the formulas for the masses are actually universal in the sense that they apply to both of the distinct phenomenological situations, which is kind of unexpected. We also see that we can have decoupling, so we can either decouple both to a standard model and high masses, or we can go to HDM limit. But then again, we are not completely free to just choose the masses as we want, and they follow a very simple relation. Indeed, the charge, in terms of tiers, so the charge scalars and the neutral scalars, and the neutral scalars between themselves are actually follow, so they have a fixed splittings. And these fixed splittings must be identical to both of the tiers. And lastly, we find that we can decouple this into two different tiers. So basically, the lightest multiplet, let's call it, stays at the scale of U2, and the heavier stays at the scale of mu3. Now, all of this, we assume that the minima we chose to preserve remained global. This was true in the symmetric case because they were degenerate and overlapping and all of that, but the soft breaking terms completely destroy the symmetry, and this means that the minima are no longer equivalent. And then our preserved minima is not necessarily global, and so we employed basically a numerical study to see if we could say something about this, and we find the simple sufficient condition to for the minima to remain global, which is just to have the eigenvectors to be positive. Now, they can be slightly negative, but the frontier is blurred, and so no strong statement can be taken. Right, so in summary, large groups are very restrictive, and so we decided to introduce soft breaking to introduce some flexibility into our model. But we chose to take advantage of the fact that they have a very rigid minima structure, and we chose to preserve it. And although there are no residual symmetries, we found that the freedom we gain is very constrained, which seems to be like inherited properties of the symmetric potential. We find that the degeneracy we have in the symmetric case lifts, but it lifts in a constrained way, which is universal for all of the minima of the symmetric potential. And of course, in terms of classification of soft breaking parameters, this is just a first step. We only dealt with 4 of the 9 possible parameters, and so more is to come. All right, thank you.
Okay, thanks a lot for this nice talk and being on time or even too short somehow. Are there questions from Zoom? I don't see any questions from Zoom. So in the audience, many questions. I start again with Gustavo.
I was surprised by some of your results. Is there any reason for that? Is there any way of understanding quickly and easily why the model that you considered does not lead to spontaneous equivalation? Because with 3x doublets, the simplest possibility is to introduce C2 type symmetries, and for 3x doublet, contrary to what happened with 2x doublet, you can have spontaneous equivalation. Very simple model based on Z2 and all that. What is motivation to consider very large groups that they are not even able to obtain spontaneous equivalation? That's one of the motivations to go to more than 1x doublet. As you know, the first multi-X model was suggested by T.D. Lee, that they put 2x doublet suggested to get equivalation. Now we are saying that with very large symmetries to fill everything. So let me be fair. Why to start such situations of very large symmetries?
Because it leads to very strict predictions on the scalar masses, and so if you find something, then you have smoking guns all around. So if let's say you find an extra scalar, then if you have a sigma 36 or even a softly broken sigma 36, then from there you're very restricted, and you can easily kill very easily your model.
Yeah, Apostolos just sitting behind. That's maybe.
I don't know if I saw the questions here from Gustavo. So first of all, the largest symmetry of maximal symmetric Higgs doublet models
It's not sigma 36, but it's SP6 in your case, epileptic group 6, which we consider more than a month ago before your work appeared, which we have similar relations because of the constraint. Of course, in this case, you have one quartic coupling, just one quartic coupling, and you have quartic coupling unification. I hope this gives motivation to Gustavo to consider these models, quartic coupling unification. Right. So, the point is also in this case that you also can break the symmetry in any direction you wish. Okay. So that means the soft breaking parameters do not need to satisfy a fine-tuning condition like you have there, because to find an alignment, you need a condition which is a fine-tuning. All right, so you don't seem to get rid of them, and you already know that there are only 3 continuous groups that could evade these problems. Right, so the question to you is, as we already discussed, at which scale you expect this sigma 36 to take place? Is in the, I mean, as far as I understand, the Yukawa interactions do not preserve that symmetry. So I would expect to tell me at which scale I would expect that kind of symmetry to hold. Generalization group scale.
So this is not, so that's a very phenomenological question, right? And this is not a phenomenological model. It's more of a...
When you impose symmetry, say, over what scale the symmetry is imposed, at least unless it's an exact symmetry. In your case, it's not an exact symmetry.
Yes.
So it's not correct.
I mean, to answer, so you want to know...
The black scale is in the...
Well, that depends on the coupling with the fermions and all of that, which is something we didn't look at. We just wanted to look at the... Sure. I mean, you can write, you have freedom, like that probably should be related to the soft breaking terms if you think of it as a spontaneous symmetry breaking, and then you adjust the scale of new physics through there, I guess.
Yeah, I understand. This exercise you need to do.
Okay. And maybe you should have this discussion over coffee. I think there was one more question. No, Bogdan is... your question has been answered or has disappeared. Okay, another very quick question. Would I suggest you to continue this over the coffee break? So thanks again for your talk. We have the next speaker, sorry, Miguel Bento. Okay, in person. Very close to your. You can take off the mask during the talk. Good. It's the invariance. You have it very close, otherwise. Okay. Maybe. Yeah, yes, maybe. Yeah, yeah, okay. This is the pointer. Okay, very good. We are happy to have Miguel Bento here talking about invariance of multi-Higgs doublet models. So you have 18 minutes. After 13, I will give you a warning.
Okay. So this is a talk about multi-Higgs models, but it is not a talk about multi-Higgs doublet models. So this is a talk about invariance. This is a talk about how to find physical parameters when we have a theory with many parameters. So I'll give you a small motivation for the talk. And then I'm going to discuss a little bit of mathematics, an example in the 2 Higgs doublet model and an example in the 3 Higgs doublet model, and some properties. So we build a model. We have many parameters, some will be related to physical parameters. Some are phases that don't matter. But CP, for instance, is a physical property, or it exists or it doesn't exist. So we should be able to measure it with physical parameters. But there are less physical parameters than there are parameters. And these in turn can be built from the action, from invariance of the action of a group, basis group. Okay. So invariant theory in mathematics, what it means is we have some parameters that transform under a group, and we want to find these invariants. In physics, what this means is that we are trying to find physical quantities. So it just seems very easy because we know that we can take traces or determinants, and we all know that that will yield invariants. But of course, that's not so simple because, for instance, in CP violation in the 2 exabot model, we have 4 conditions, and we, in principle, could have been able to write 10 necessary conditions, but not 10 necessary and sufficient conditions. And for that, we have invariant theory, which gives us a framework to try to find the generating set for these properties. And what we do is to begin a theory with a certain set of parameters V. So in the 3 exabot model, that will be the lambdas and the mu's. And observables will certainly be polynomials or related to polynomials of these parameters. And polynomials that are invariant are what I call CVG. This is just the set of polynomials that are invariant. So these are the physical parameters of this theory. So how does it work? It works by beginning to find the scalar potential that we want to work with. And we have to know how the Y and Z tensors transform under the, I can call it the basis group. So it will be SUN, of course, because this is also the most general any exabot model, always. So these irreducible representations will be building blocks, and with these building blocks, we construct invariants, and these invariants will be physical parameters. But we also need to compute something called the Hilbert series, and it has been used before to construct, for instance, page invariant operators in effective field theories. And this Hilbert series will give us the generating sets. I told you something about the why, but why though? Because, for instance, there is a model, and I have it here, is the 3 exabot model with CP4, which has complex perimeters, but it's CP conserving. So this is a very, not obvious, but somewhat obvious example of what I'm trying to say is that we may have something that appears to be a property of the model, but it's not, because it is not a property of the space of the physical parameters. And the example I had before about trying to find, for instance, the necessary and sufficient conditions for CP violation in the 3 exabot model. And this one I will talk about later. Okay. Well, it seems like a good idea, but is it possible to do that? And sometimes, not often. Because the Hilbert series is a very complicated calculation. It is a series of complex integrations. When we start the 2 exabot model is just one, it's a residue theorem. Anyone knows it, anyone can do it. The integrand is an exponential, what I call the platistic exponential, but it's actually a rational function. So it takes as parameters the weights, the characters of the group, of the basis group. There will be examples. 3-hexabyte model. So all of this has been done by Andreas Trautmann. And Andreas Trautmann, in his work, he broke Y and Z into representations of SU2. And he computed the quantistic exponential, which is equation 3, and he integrated it. Okay, in equation 4, it's just the characters of SU2. So it's very simple, you integrate and then you have equation 5, and the numerator is not very important, but the denominator is very important because the denominator tells us that the generating set for invariance, and this means the generating set for constructing physical perimeters, has 3 linear invariants, and always be factorized from the integration. 4 degree 2, 3 degree 3, and 1 degree 4 invariants. So this tells us something about the structure of the 2-hexabyte model in terms of physical parameters. So if we know these 11 physical parameters, we know the model, we know everything about the model. And in turn, this made also possible to know the necessary and sufficient conditions for CP violation in the 2-hexabyte model. And yes, I know this is known, but this is an attempt for the 3-hexabyte model. So, don't be scared, this is just how Y and Z always break in n doublets. So this is just a table. The only thing that will be relevant is that I will use n equals 3. But contrary to the 2-hexabyte model, in the 3-hexabyte model, there are 2 counter integrations, which may seem simple, but it's not, because you do the first one and then you have quartic cubic roots, and then now you have to take care of branch cuts and all of that. So the solution was something that was invented by many people, but there is a particularly fast method by Guaxiachin, which is a mathematician, and it uses integral partitions. It's not very important. There is a program in Maple and you can do this in 1 hour. And okay, the result is very bad because the numerator is very bad, is very large, but the denominator does have the structure of the generating set of the physical parameters in the 3-hexabyte model, which is, for instance, there is 1 degree 9 physical parameter which belongs to the generating set. But the numerator involves very large coefficients, but also we learned that there are 36 invariants, that is physical parameters in the 3-hexabyte model, which was already known. So I'm not sure if this is known, but the correct formula to derive the 46 is this one that I have above, which gives the second n to the power 4 and to the power 2 plus 2 divided by 2. And the reason why I don't think it's very well known is because that last term there is almost always 0 in any hexabyte model, so most people only subtract the basis, the dimension of the basis invariant, the basis group, actually. So this is a very long road still, but we already know the structure of the invariance of the 3-hexabyte model, and what we hope is to get the necessary and sufficient conditions for CP violation in the 3-hexabyte model with or without symmetries. Okay. So there are conclusions, but there are many conclusions. The conclusions is there are 36 invariants, and these are the generating set, and we can build them, actually. And the other conclusion, because this is very something that may have not been noticed, but there are always 3 singlets in any n-hexabyte model, so there are always 3 physical parameters, and so the maximum symmetry that you can do in an n-hexabyte model leaves us with 3 physical parameters. And that's it. Questions?
Thanks a lot for this nice talk. Other questions on Zoom? I don't see any question on Zoom. Other questions in the room? It's always the same people. Very good, Gustavo. At least they're very good questions.
One make, anyway, it's very nice work, but I don't want to do a criticism, okay? That is, has to do with the following. We do these things in order to make predictions, but they are only valid if when you use symmetries, when you apply to the full Lagrangian. When you're doing, for example, applying this symmetry only to the expression, predictions of these symmetries are not stable, you see, because Yukawa couplings violate these symmetries, you see. So you have really to be, although it is not as fancy from a mathematical point of view, you should study in order to be contact with physics, not just to mathematical manipulations. You have to include the study of Yukawa couplings, you know. It's crucial. Otherwise, you know, you cannot, for example, in a previous speaker, they were saying that, okay, if we discover Higgs and we studied this symmetry group, sigma 36, you know, like Miguel, then we will know that this is it. This is nonsense, you know, because you have not included the Yukawa couplings. Until you include the Yukawa couplings, you cannot talk about, we're going to discover Higgs. They are going to decay into what? Into fermions. So that is controlled by the Yukawa couplings, okay? That's all my it's very good, but it should include, even in a smaller work for physics, you should include the Yukawa couplings, always.
Okay. You need to talk, okay. Please.
Which is also working with these aspects intensively with Neda Tarvisi, also with some experimental physics, do 2HDM and 2HDM EFT as well. Okay, right. So I agree with Gustavo fully with the Yukawa couplings, which was also the comment from people, which is important when you have symmetries. As far as I understand, in your scenario, you don't have any symmetries, because you can play free and you just try to count the number of quartic couplings, which we are calling physical or whatever. And you already know from our paper in Nuclear Physics B that we already counted them in a naive way, okay? I don't know what else you can tell me from your approach, apart from this, of counting the quartic couplings. It's already counted by way all these formulae are there.
What do you mean about counting quartic couplings?
Quartic couplings, yes. I mean, just
in which way?
In any Higgs doublet model. So you can count the reparametrization. You can reparameterize the freedom-free parametrization. You can remove. You can count the combination of the quartic couplings. Subtract the reparametrization group, which is SG1 for any Higgs doublet model, and you find the number of couplings. I don't need to do all this machinery. So what else do I know? Do I get? Do I learn from your approach apart from that, which I can't do in a different way?
Because this is not that method is not trial by. It's not trial and error, but it is not systematic. The approach of having a specific model and the rephasings, trying to find the physical parameters, how many physical parameters are there, it's not systematic. Because in this approach, right?
This is what people did over here.
Okay. But that's, you have to do that for each model. This is for all Higgs open models.
For a class of n Higgs doublet models.
Yes, with or without symmetries.
Okay. Okay, I think we have a topic for discussion round, to our discussion round or some later. Okay, very good. I think there were two more hands. I don't know who was first. I just go by the order. Yeah.
So near the end of your talk, you mentioned that you know how to build the invariants. You actually have the expressions in terms of the y and z, the contractions of the indices to make the 50-something invariants for the.
Okay. In which slide do you know?
It was near the end, and you said there's like 50-something for the 3 Higgs. Yeah, there you can see all that there's, for example, 4 invariants of order 12, shall we say, right? But I think you said 46, not 50-something. But I think you mentioned that you knew how to build them, or you have the contractions of the y's and z's that correspond to each of them?
Yes, so I wasn't able to put everything into the talk, but there are many more frameworks to this, and one of them is a complete list, not generating set, but a complete list of everything that can be built with places that is invariant under a specific group.
Did you sort them into CP violating and not?
Actually, that can be done with the 2 exabyte model. It was done, but in the 3 exabyte model, it is not possible now.
Okay, Bogdan?
Yeah, I agree with Apostolos and Gustavo as well that this machinery doesn't, it's not useful for counting number of parameters. Right? However, I disagree with Apostolos that the form of invariance is useless in terms of other parameters. Because then one can easily study, for instance, CP violation, right? You're taking invariants that are sensitive, that vanish in the CP conserving case, and then it's easy to systematically search through all those combinations.
I agree that you have some invariants actually, but polynomials that actually properly classify all symmetries.
Can you wait one?
The way you classify all the symmetries discrete, I think Ivanov and continuous and discrete is exactly using what we're calling primary invariants, which you see the Higgs doublets. It would be nice to see them, I mean, rather than having only numbers here in your talk. And in there, you can see really that you have this CP4 symmetry. You can see the polynomial has complex coefficients. You cannot break it because you break the symmetry. And you use that as a building block with real coefficients to construct the potential. So you construct the potential with polynomials. And these polynomials you cannot break. They have complex coefficients. So not with monomials, but with polynomials, with real coefficients.
Okay, I think there's still a lot to discuss maybe later. Okay, thanks. Let's thank the speaker again. And let's move on to the next talk. Also in person. Good. So this is there's the microphone.
Do you hear me? Yeah, I think yes. Oh, I uploaded to the Enrico page. Yeah. Yeah, that's one. Okay. Do you hear me?
Okay. Okay, very good. Let's continue. So now it's a pleasure to have an experimental talk by Mohamed Belfkir on the search of Higgs boson pack reduction in the 2 bottom quarks plus 2 photon final state with Atlas. So as before, you have 18 minutes. After 13 minutes, I will give you a warning. Yeah.
Okay, thank you. Yeah, so thank you for the invitation, and I will give a talk on behalf of the Atlas collaboration on the search for the Higgs boson pre-production in the BB gamma final state using the Atlas detector. So the Higgs boson production is an event where 2 Higgs bosons are produced in a single proton-proton collisions, and its cross-section is 3 orders of magnitude smaller than produced in a single Higgs boson. And it's a very challenging process because, and it's not observed yet while limit on its production cross-section are set. And this very low cross-section could be enhanced by the presence of the beyond standard model physics that could manifest either as a deviation in the variation of the Higgs self-coupling, which called no-resonant enhancement, or as a new particle that decay to 2 Higgs bosons, which called which define the resonant enhancement. So starting with the Higgs self-coupling in the standard model broken phase, the potential of the Higgs can be parameterized as this function. And the first term is the kinetic term or the mass term of the Higgs boson. And the second term is the trilinear coupling, which define a vertex with 3 Higgs bosons. And the last one is the quadratic coupling, which is a vertex with 4 Higgs bosons. So it's not accessible at the LHC. So I will be focusing on trilinear coupling, where the amplitude of the vertex is proportional to lambda. And lambda is related to the mass of the Higgs boson with this formula. And in the rest of the presentation, the word self-coupling refers to Higgs boson trilinear coupling lambda, which is a very important and interesting parameter because it controls the shape of the Higgs potential. And in the standard model, and given the precise measurement of the Higgs mass, the lambda is about 0.13, and it should be verified experimentally to check it if the lambda here is similar to the one defined by the standard model. And also the presence of BSM anomalies can modify this coupling, this very small coupling, and the modification is quantified with the kappa lambda modifier. And this modification, this BSM could manifest as a deviation in total cross-section, as you can see in the plot. I don't know if it's visible, but it's the total cross-section as function of kappa lambda for different production modes. And the minimum you see here is related to the destructive interference between the Feynman diagrams, and also as a deviation in differential cross-section, as you can see from the schematic of the invariant mass of the 2 Higgs bosons and the impact of each parameters on this distribution. So in this case of the non-resonant search, we are not looking for new resonant that decay to Higgs, but we are looking for a deviation in the kappa lambda measurement to indicate the presence of BSM physics. And this is only accessible directly with the production of 2 Higgs bosons, which is mainly produced at the LHC via the non-resonant gluon-gluon fusion vector boson fusion through these Feynman diagrams, where you can see the direct access to the kappa lambda parameters. And also the resonant gluon-gluon fusion with the spin zero decay that decay to 2 Higgs bosons. And in this search, the mass of the particles is taken to be from 251 GeV to 1 TeV. The matrix here presents the different decay channel of the Higgs event, and the largest one is the 4B, where both Higgs bosons decay to 2B quarks. And one of the most sensitive is BB tau tau, where one Higgs boson decay to 2B quarks and the other one decay to 2 tau leptons. But in this presentation, I will be mainly focusing on the Higgs to BB gamma gamma final state, where one Higgs decay to 2B jets and the other one decay to 2 photons. The branching ratio of this channel is about 0.26%. Even with the low branching ratio, it is one of the most sensitive channels. It's a golden channel because it compromises between the high branching ratio from Higgs to BB bar and the very clear signature of the 2 photons in the calorimeter. So basically, we are looking for a signature of event that's look like this one, 2 photons in the calorimeter and 2 isolated B jets. This is not the first time this analysis is performed, because it's what was already performed using a fraction of N2 data collected between 2015 and 2016, which correspond to an integrated luminosity of 36 inverse bar. And today I will present the search with the full N2 data collected between 2015 and 2018, corresponding to 139 inverse bar. And to give you an order of magnitude on how much event we expect to see in this data, if we are in the standard model and the standard model expectation holds, we expect to see 4.3 thousand events of Higgs in all its production channel. While if we are focusing on BB gamma gamma final state, we left only with 11 events. And for an efficiency, for analysis efficiency, of the order of 10%, which is roughly what we have in this analysis, we left only with around 1 event. So we don't expect to see any Higgs events in this data, while these numbers are enhanced by the presence of BSM anomalies. So starting with the trigger, firstly, our events are triggered using biphoton trigger with an efficiency of 83% for standard model signal, HE signal, and 70% for the resonance signal. And they request to have at least 2 tied and isolated photon to construct the Higgs to gamma gamma components. And the 2 leading photons are used to build in gamma gamma variable, which satisfies the cut from 105 to 116 GeV. And they are requested also to have exactly 2 jet to reconstruct the Higgs to BB bar component, and the beta is performed at 77% efficiency per jet. And the specific B jet energy correction is applied to the B jet to improve B resolution. The plot here shows the invariant mass distribution of the two photons in data and Monte Carlo, and the dominant backgrounds for this analysis is the single Higgs to gamma gamma in GGF and TTH and ZH production modes, and the largest continuum gamma gamma plus jet. Additional cuts on the number of leptons and the number of jets in the events are applied to reduce the contamination from TTH. This cuts or this preselection is common between resonant and non-resonant analysis. So even with this, the resonant and resonant analysis use different categorization. So starting with the non-resonant categorization, events are split in two mass regions defined on the MBB gamma gamma star variables defined with this formula. A high mass region that target the standard model signal to be the best limit on the cross section, and the low mass region that target the BSM effect on the self-coupling to be the best kappa lambda interval. And in each mass region, the signal is separated from the background using a boosted decision tree, and each one trained to separate the signal from background, sorry. And both BDTs use different signal hypotheses. The one trained in high mass region use the standard model as a signal, while the one trained in the low mass region use the kappa lambda 10 as a signal, but both use similar inputs for the training coming from mainly from the object and event kinematics. And the bubble chart you see here is illustrating the different variables used in the training, and the size of the bubble illustrates a bit the importance of these variables for the training to separate from the signal, to separate the signal from the background. So the most important one is the invariant mass of the 2B jet. So then four analysis categories are defined to maximize the combined expected significance. Applied and blues categories in each mass region. And the plot here shows the BDT score in the high mass region, and the dotted line define the boundaries that define the tide and the loose categories. So this is for the non-resonant categorization. And for the resonant categorization, it's also relates on two BDTs, but this time each BDT is optimized to separate the resonant signal from a specific background, the BDT gamma gamma to separate the signal from the continuum gamma gamma plus jet background, and the BDT single Higgs to separate it from the single Higgs. And the both BDT are trained inclusively for all resonance masses, and then they are combined in a single BDT score in quadrature using this equation. And the plot here you see is the combined BDT score for the reference of 300 GeV mass resonance. And then one category is defined to maximize the expected significance per resonance. As you can see here, the boundary for this 300 GeV, and then additional cuts on the MBB gamma gamma star variables are applied on the plus minus 2 sigma, plus minus 4 sigma for high mass region to allow for more statistics. So after the categorization, if, the signal is extracted from data by performing a simultaneous fit of the invariant mass of the two photons. For the non-resonant and resonant search both, where the di-Higgs signal, which combine Glion fusion and vector boson fusion, single Higgs, and the resonant signal are estimated and modeled from Monte Carlo using a double-sided crystal ball function. And for the non-resonant search, the number of events is parameterized as function of kappa lambda to allow for the scan of kappa lambda and measurement of kappa lambda. And the continuum gamma gamma plus jet background is fully driven from data using a smoothly analytic function. And the bias from the chosen of the function is estimated, is quantified using the superior signal test, which is used as systematic uncertainty on the background modeling at the end of the analysis. So here I show the non-resonant result, and the plot show the background only fit of the data in the most sensitive category, which is the higher mass 5 BDT category. So no significant signal is observed over the background only hypothesis. So then limit on the di-Higgs production cross-section are derived or computed as function of kappa lambda, and the plot show the observed and expected limit on the di-Higgs cross-section, the GGF plus VBF, as function of kappa lambda compared to the theory. So a limit of 4.1 times the standard model expectation is observed on the di-Higgs cross-section, production cross-section, and from the intersection between the theory and the computed limit, kappa lambda interval is derived to be from minus 1.5 to 6.7 for kappa lambda, and it is the best limit on the kappa lambda up to the moment. So just to highlight that the analysis is statistically limited and the effect of systematic is about 4%, mainly coming from the background model and the photon energy scale. With respect to 36 and over the previous one, this analysis brings an improvement of factor 5, where a factor 2 is coming from the increase of luminosity and almost factor 3 is coming from the different analysis improvement, where 80% is coming from the new image age categorization and uses of NVA in the separation between the signal between the background, and 7% is from the improvement of the MBB resolution using the BJT energy calibration, and also there is different improvement coming from the collaboration. So for the result, no significance exists over the background only hypothesis is observed, as you can see here from the background only effect to the data in the 300 GeV mass resonant. So limit on the production cross-section of the X particle are set for different masses, and the observed limit is ranging from 610 femtobar to 47 femtobar, while expecting 360 to 43 femtobar. And also this analysis is statistically limited, and systematic effect is up to 10% for some masses, and it is mainly coming from also from the background modeling and photon energy scale uncertainties. This analysis brings an improvement of 30% coming from the usage of BDT with respect to 36 and femtobar on top of the luminosity increase. So this brings me to the summary. I presented the no-resonant and resonant search for di-Higgs to BB gamma final state using the full run to data, and I want just to highlight that there is also other channels that are published, the 4B, the resonant 4B, and the resonant and non-resonant BB tau. And also recently, a comparison between the non-resonant search and the resonant search are also published, where you can see here that the most sensitive channel are BB tau tau and BB gamma gamma, and here you can see the different impact of each channel in the low and high mass and for each channel. So we did a great improvement in the full run to data, and we are almost optimistic to see what will happen for the next round of analysis, the run 3. I think that's it. Thank you for your attention.
Yeah, thanks a lot. Other questions from Zoom? I don't see any hands from the room. Any questions? Okay, I have one. Oh, sorry. Okay. We need yeah, please. Thanks.
There will be questions, right? What do you expect to learn from this non-resonant production? And what do you expect to learn from this non-resonant production? And especially you mentioned that the background is fully data-driven. That means that you don't study the background, it's just taken a little bit off the side to give it. So if there is something in the background, you will not see it.
Well, we know exactly what is the background from the search for from the single X, because it's the continuum one. Because it's the continuum one. So we already studied in the last round of the round 1 and the round 2 also. So we know. Wait, what is not one?
Can you let him? Yeah.
Yeah. Up. So we know exactly this analytic this shape of the background. So we don't need to study it.
Sorry, but you know the shape of the background because you fit a function to the background, not because you understand the background.
No, it's from theory. Because if you are producing 2 photons randomly, the energy, the invariant mass will fall will have this shape.
I remember the bogus gamma gamma thing, and there was also an analytic formula interpolating the background. And within 6 months, this formula varied by a factor of 2.
Okay, maybe more detailed discussion at some point.
For the non-resonant search, I think it is important to know the self-coupling of the Higgs, the coupling of the single Higgs. It's another search it's another way to search for B's in physics in an indirect way.
Okay, any more questions or comments from the audience? No, okay. I have in fact 2 questions. So the first question is, how did you simulate this? I mean, for this DIHIGS, there has been extensive work, I think also including higher order corrections, a lot of development. There are some DIHIGS benchmarks within EFT and so on. So what did you use?
Okay, so this slide resumes the different simulation. So basically, for the standard mode, for the HH, the GGF and VBF are simulated. The GGF1 is simulated in the net at any low, and we simulate 2 points. Then we use a modeling of the reweighting to reweight to the other kappa lambda values, and this reweighting is coming from theory. This is developed by theorists. For the VBF, it's we use leading order, and it's the same approach. Then, yeah, for the resonant one is the math graph, basically at leading order.
Okay, but you only vary kappa lambda, right? I was thinking about a more generic kappa, but you keep everything to the standard model apart from this kappa lambda.
There is a reweighting that we weight the event to different kappa lambda values. So we get the shape.
Yeah, but you don't have kappa top, for example, and so on. Okay, very good. And the second question for your summary slide, maybe. I mean, I was showing earlier comparison to the combination which you have here, this combined early 1-2 data, which I can't really see now, is the black line somewhere. So, and there are now quite a few new results, and especially here in the high mass, it looks like you go down by an order of magnitude more or less. So do you know the timeline for full combination for 1-2?
Okay. I'm not sure if I'm allowed to say this, but there is an ongoing combination, and I think it will take almost half of a year to have the full combination of the different channels.
I mean, one can kind of guess which channel is dominant where, right? But
so the domination is different in specific mass regions. For example, in the low mass regions, we benefit from the BB gamma gamma because of the low trigger, and in the high mass region, the 4B, the boosted one is the most dominant, but in the middle it's only the beta. Different channel interface.
Very good. Are there any? We have 2 more minutes. If someone has another comment or question. No? Okay, very good. Let's thank the speaker again.
Thanks a lot.
I think this is the first fully in-person session of this workshop. It's fantastic.
On the red one. It's big on count. Is it working?
Okay, so we have the last talk of this session by Bernardo Gonzalez. I hope I said correctly. Yes, good. Some reflections on hidden features of standard number extensions with scalar triplets. As before, you have 18 minutes. After 13, I give you a warning.
Okay, thank you. So good afternoon, everybody. My name is Bernardo Gonçalves. And first of all, I would like to thank the organization for the opportunity to present my work here in person. And so, as we all know, on the 1st of July 2012, the CERN has announced the discovery of a Higgs-like particle, and so the standard model of particle physics became completed. But as we all know, this cannot be the whole story. And so today, I will bring 2 hidden features on scalar triplet extensions of the standard model, namely in the Higgs triplet model and in the 2 scalar triplet model. Regarding the first one, the Higgs triplet model, as we all know, it is well motivated by the type 2 seesaw mechanism. And today I will be interested in discussing with you if neutral minima in such a model are or not stable against charge breaking. This is the archive reference for such work. Well, in the Higgs triplet model, we add to all the standard model fields an SU2 scalar triplet. And a priori, one could wonder that we could have three different vacuum possibilities, namely CP breaking, charge breaking, and normal neutral vacuum. But it is not possible to have CP breaking vacua in the Higgs triplet model, and so we are left with a question if neutral minima can or not be stable against charge breaking in such scenario. Well, this is the most general gauge invariant scalar potential one can write. Here we have the quadratic and then the quartic terms, and here we have a cubic term that softly breaks this U1 symmetry. And we will be interested in studying this question in both cases, with and without this soft breaking term. We have three different possibilities for neutral vacua, N1, N2, and N3. N1, both fields acquire a vacuum expectation value, both the doublet and the triplet. N2, only the doublet acquires a vacuum expectation value, but N3, only the triplet acquires a vacuum expectation value, and of course, this is an unphysical vacuum type. Well, regarding charge breaking, we have 6 different possibilities. We can always render our doublet to be real and our charge component to vanish, and so we will only be interested in charged vacuum expectation values in the triplet field, and we get 6 different possibilities. And with this, we use a bilinear formalism similar to the one developed for the 2HDM in order to try to get analytical formulae relating the depth of the potential at different extrema of the potential. I will present 2 examples. The first one, the stability of minima of type N1 against charge breaking 1. Here we have both N1 and charge breaking 1, and after applying such bilinear formalism without the soft breaking term, we get to this expression over here. And this mass squared you can see here is calculated in minima of type N1, and so as you can see, if N1 is a minimum, this is always positive, and so we get that stability is guaranteed in this situation. However, when we turn on the soft breaking term, this is not the case, because we get this new term over here, and in fact, this specific term here does not allow us to say that this is always positive, and so even if N1 is a minimum, it is not guaranteed that this quantity is always positive, and stability cannot be assured. We have done this thing together for all the charge breaking type minima against N1 and N2, and so far this is our results for stability. When we do not have a soft breaking term, stability is always guaranteed against charge breaking in N2 or N1, but when we turn on such soft breaking term, stability is not guaranteed. However, as we may have noticed, we have worked with C1, which is the vacuum expectation value of the doublet of the charge breaking vacua, different from 0. But in fact, there exists another disconnected solution from this one, which is the case of the Webless doublet. And since those solutions are disconnected, we cannot simply put C1 to 0 previously, and so we have to perform all that formalism again. So we get 6 new possibilities for charge breaking vacua. They are basically the same, but now we have a completely Webless doublet, and we again perform a bilinear formalism. In this case, I will not present any example because we get similar expressions, but in this situation, we are not able to say that any of the expressions we obtain are always positive, and so stability is never guaranteed in the case of the Webless doublet. These are our final full analytical conclusions, and then we went up to do a numerical scan. First, without the soft breaking term. Without such a term, we can guarantee that the N2 minima is stable against N1 minima by simply analytical reasoning. And so, but N2 is not necessarily stable against charge breaking with the Vevel's tablet, like we have previously seen with analytical reasoning. And we have actually identified that the most likely charge breaking vacua combination in these situations are these ones, CB7 and CB10. This is a plot that we have obtained that you can see here, in which we have the dark matter mass versus M squared. And apparently, since you can see here in blue, in red, we have the points in which there exists a charge breaking vacua, which is lower than M2. And so in blue, we can guarantee that we have stability. We have apparently here a clear distinction regarding these two parameter zones. Actually, we have shown analytically a condition that guarantees full stability of an M2 minimum against charge breaking. And indeed, in our numerical scan, we have found out that this condition is M squared positive, and this is how we can see clearly the parameter space in which we have full stability. However, this is not the situation, again, when we turn on the soft breaking term. In this case, N2 minima is not possible to occur, so we are only interested in type 1, in type N1, and in this case, indeed, there are several possible deeper charge breaking vacua, and again, the most common ones are CB7 and CB10, but as you can see by this plot, in this case, we do not see a clear distinction between the area or the zones of the parameter space in which we have or do not have stability. And so to conclude this first part of my presentation, yes, charge breaking global minima can indeed coexist, and in some cases fairly frequently with neutral minima. Now we go to the two-scalar triplet model. This model is mainly motivated here because it's the minimal triplet extension in which spontaneous CP violation can occur. And so maybe this is a way to communicate spontaneous CP violation to the fermionic sector. But what is happening in the scalar mass spectrum before we try to do that? This work will still be out quite soon. Well, as I told you, in the Higgs triplet model, by the minimization equations, we get to this expression, and by this expression, we get no spontaneous CP violation. However, in the two-scalar triplet model, we have decided to work in a U1 symmetric potential added with softly breaking terms. And in this situation, with such vacuum configuration you can see here, we get, again, by the minimization equations, to this expression over here. And with this expression and with θ1 different from θ2, we indeed see that spontaneous CP violation is possible, and so it can be communicated to the fermion sector. But again, what is happening in the scalar mass spectrum? Well, we have used results from matrix theory, mainly to see if analytically we can have some insight regarding the eigenvalues of the squared mass matrices, and so the square scalar masses. We expect, of course, 6 neutral scalars, 3 singly charged scalars, and 2 doubly charged scalars. Well, in the CP conserving scenario, we get what we were expected: 2 Goldstone bosons, 1 Higgs-like particle, and all the remaining particles decouple. However, this is not what happens in the CP violating scenario. We also get 2 Goldstone bosons and 1 Higgs-like particle. But we have here seen that regarding the 2 mass states before the Higgs-like and after the Goldstone boson, we were able to get these results only using matrix theorem results, and this result is exact. And as you can see, if all these parameters here are combinations of party couplings, and U, which is the scalar triplet VEV, which is constrained to HEV, this is bounded. And so we have 2 neutral scalars that are bounded, and so we expect 2 light neutral scalars. Regarding the charge and doubly charged spectrum, we also have obtained an interesting result. First of all, we have obtained a relation between 1 singly charged and 1 doubly charged scalar, and both of them are proportional to the doublet's vacuum expectation value, since all of these expression has party couplings and some functions which depends on these angles. And so we also expect two charged particles at the electroweak scale, and indeed all the remaining particles now decouple. These are our final full analytical conclusions, and as you can see in the CP violating scenario, we indeed get two light neutral particles and two charged particles at the electroweak scale. The same color that you can see here in this table indicates that such particles are nearly degenerate. Then we have performed a numerical scan in order to ascertain our results, and indeed we have here the numerical confirmation of our analytical bounds for those two light scalars, as you can see here in blue and in orange. And also we have seen not only the relation between the singly charged and the doubly charged masses, but also, yes, they are in the electroweak scale. And so our analytical results have been confirmed. But of course, up to this point, one could wonder and must wonder if such scalars could or could have not evaded detection. Well, first, we have looked up to the light neutral scalars, and we have plotted its couplings with the Z boson, and we have used the limits from lab when they were looking for scalars, namely non-standard scalars. And indeed, we have a lot of parameter space that we have obtained in our numerical scan that is below such limits, and indeed those scalars could somehow have escaped detection. We have used just the points that are below such limits, and then we have generated also points regarding the singly charged and also doubly charged particles. And since the charge component of the doublet is the only one that couples with the quarks, we have plotted the inverse of X2, being that this H2 is the electroweak one, H1 is the goldstone, and H3 decouples. We have plotted it against its mass, and we have used the most restrained bound from B to S gamma. And as you can see, all of our points are above such line. We have also used a bound from the LHC regarding the doubly charged mass. But as you can see, since we have a relation between those masses, what we would get is would just be with a different limit that these different colors would separate at different points in this plot. But we are still interested in seeing if somehow lepton flavor violation processes could impose a lower bound on the triplet SVEV. And also, of course, since we have an upper bound on such light masses that are proportional to the triplet SVEV, if we try to explain neutrino masses, then we would get really light scalars. And so we are wondering if we can indeed simultaneously explain all of these things, neutrino masses and leptonic CP violation, through spontaneous CP violation in such a model. And I am questioning if this is true or can be true for any number of triplets, 3, 4, and so on. And so to conclude, I started with 2 problems and 2 questions. And I believe that the main take-home message in this situation is that in the Higgs triplet model, yes, charge breaking global minima can indeed coexist with neutral minima. Of course, tunneling probabilities must or could be calculated. And in the 2-scalar triplet model, when we have spontaneous CP violation, such model has no decoupling limit. Thank you.
It works, sorry. Okay, thank you. Questions on Zoom? I don't see anything on Zoom. Questions in the room? Bogdan?
So I missed something. What do you do with the T parameter if triplet VEF is non-zero?
Sorry?
the tip parameter. It's what? No, okay. Raw or delta raw.
Yes.
So there are limits.
Yes, and
that must be small.
yes, yes. That's because that's why we impose at least it has to be smaller than HEV.
Okay, and that's sufficient.
And that I believe satisfies the role parameter. Yes.
Okay.
Okay. Do you have can you wait for the microphone? Sorry. You don't have a question? Okay. We have time. You can have a question if you want.
So, your constructions you are using on top of it, is that two symmetry? All of them are quadratic, or you can have also linear combinations of couplings of delta phi?
Sorry, can you repeat?
Maybe you have there is a reason why you don't have phi transpose delta phi, for example.
We have just worked with this potential, but it's not the most generic one. Yes.
Yeah, that's what I'm saying.
Yes.
So why you are doing that?
Because we have decided to work with a more simplified form.
Formalism to.
Yes. No. We believe that the conclusions might be the same, but it's not the most generic. Most generic one. General.
Okay. Any further questions from Indico? Sorry, Indico from Zoom or the audience? Okay. Do you have a question? Yeah, please.
Can you go to the relation between the double charge and the charge mass?
Here.
Yeah. So you say that that must lie on the electric scale, right?
Yes.
But can I tune phi 1 and phi 2 to get a small parameter?
Phi or F?
Yeah, to get a small denominator and try to decouple it that way.
I don't think so, but I will have to check the exact formula of such expression. But I don't think so, even because of the numerical scan that we have performed. Yes. Yeah.
Can you, if you want to say something longer, can you take the microphone? Yeah, still, the people on Zoom want to follow maybe.
It's a standard model there, right?
Yeah, it's the doublet web. Yes.
If you have something, I mean, to decouple that with a very big coupling in front, you have to, I mean, I believe the only way to do it is to make large some of the quartic couplings.
Yeah.
Like PXDN would be lambda 5, for example, whatever. But here you take, you have a cancellation, looks like a very bizarre situation. But okay, it shouldn't happen. That would be a consistency check of your analysis.
Thank you.
Okay. I have a question if there's no one else in the room. So maybe. Okay. I'm telling you. No, please go ahead. I can ask in private.
Can you hear me? You said that with that soft new parameter equals to 0, you have dark matter, and you don't have it with that non equal to 0. I can you elaborate? Just I didn't understand why is that.
Because you're right, the dark matter. Because when we do not have the soft breaking, we have the pseudoscalar and the capital H to be degenerate. And they are good dark matter candidates in that situation because the soft breaking is 0.
And the soft breaking like splits them. What is the soft breaking doing then?
The soft breaking is preventing them to decay, I think.
If the soft breaking prevents them to decay, they can be dark matter. What I don't understand is how can a bilinear term affect the stability of
bilinear?
It's a mute. Is it a mute term? Is not a mass term.
No, it's a
Okay.
it's a cubic term.
Okay. Now I understand. Okay, sure. I thought it was a mass term.
No, it's a cubic term.
Okay. Thank you.
Okay, I think we have to stop if there's no more urgent question or comment. So let's thank all the speakers again. My understanding is we reconvene in 15 minutes according to the schedule.